In the vastness of Chile's Atacama Desert, where the air is so dry it preserves mummies for millennia, and the nights are so clear they reveal the universe in all its ancient glory, 4 mechanical sentinels stand watch. They are not searching for life, they are searching for death. The death that might come from above, in the form of asteroids that could end our world in an instant. But on the night of July 1st, 2025, they found something far more extraordinary than destruction. They found a visitor. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. Picture, if you will, the Atlas telescopes in their endless vigil. Every clear night for years, these robotic eyes have photographed the entire visible sky with methodical precision, capturing millions of stars in their mechanical memory. Their computers process these celestial portraits with algorithmic patience, flagging anything that dares to move against the stellar backdrop. Most nights, they find nothing remarkable. Perhaps a known asteroid on its predictable orbit, or a satellite crossing their field of view. But tonight, something appears that breaks every rule written in the cosmic playbook. At 350 astronomical units from Earth, a distance so vast it places this object farther from us than mighty Jupiter, a fuzzy dot races across the heavens at 61 kilometers per second. To put this in perspective, imagine a bullet that could travel from London to New York in less than 3 minutes. Yet this is no bullet. This is something that has been traveling for possibly billions of years, carrying with it the secrets of distant worlds. The discovery algorithm triggers immediately, its digital consciousness recognizing that this object moves too fast, travels in the wrong direction, follows an impossible path. The mathematics are unforgiving. Nothing born in our solar system could possess such speed, such trajectory, such audacious disregard for the gravitational rules that govern our cosmic neighborhood. Within hours, telescopes in Arizona, Hawaii, and Chile confirm what the computers already suspect. Humanity has detected its third visitor from another star system. But here lies a profound irony that speaks to the nature of discovery itself. For 2 months, 2 entire months, NASA's TESS satellite had been photographing this very same object, capturing it in routine surveys of stellar brightness. Like a letter arriving in an unfamiliar language, the data sat unread, its significance hidden in plain sight. Only when the Atlas detection provided the Rosetta Stone of orbital calculations did astronomers recognize the truth that had been traveling through their instruments' fields of view since May 7th. Consider for a moment the cosmic choreography required for this discovery. Our visitor, which would soon bear the designation 3IATLAS, had to arrive at precisely the right angle, at precisely the right time, with precisely the right brightness to be detected by our earthbound watchers. A few degrees different in trajectory, and it would have remained invisible against the star-rich background of our galaxy's center. A few weeks later in discovery, and it would have passed beyond our ability to study it in detail. By July 2nd, the Minor Planet Center, that clearinghouse of cosmic bookkeeping, collects 122 observations from 31 observatories scattered across our planet. The international astronomical community mobilizes with a speed and coordination that would have been impossible just decades ago. This becomes the most intensive observational campaign in interstellar object history, a global effort to understand a messenger from the void. The race against time has begun, though few yet realize it. Amateur astronomer Sam Dean, working with the dedication that has always driven citizen scientists, discovers something crucial hidden in the archives. Additional pre-discovery images stretch back to June 5th, revealing why 3IATLAS nearly escaped our notice entirely. Its path had carried it directly through the galactic center's dense star fields. Imagine trying to spot a single firefly against the blazing backdrop of a city at night. Millions of background stars created a cosmic haystack that would hide any needle, no matter how remarkable. The timing chills professional astronomers when they understand it fully. Had 3I-ATLAS been discovered just 2 weeks earlier, we might have missed it entirely. Had it arrived on a slightly different trajectory, it would have remained anonymous among the stellar multitudes. The universe had delivered this gift with surgical precision, threading the needle of detectability with cosmic accuracy. But what exactly had we found? In those early hours and days, 3I-ATLAS remained an enigma wrapped in mathematical certainty. The orbital calculations were unambiguous. This object originated beyond our solar system, from the dark spaces between stars where temperatures approach absolute zero and matter exists in forms we barely understand. Yet its nature remained mysterious. Was it a wandering asteroid, blasted free from some distant planetary system by a gravitational encounter? Was it a comet, carrying the pristine ices of stellar formation from an epoch when our own sun was not yet born? The answer would prove more extraordinary than anyone dared imagine. As news of the discovery spreads through the astronomical community, a quiet excitement builds the kind of anticipation that accompanies truly rare events. Interstellar objects do not announce their arrival with fanfare. They appear as whispers in the data, as subtle anomalies in orbital mechanics, as mathematical impossibilities that demand investigation. Only 3 times in recorded history has humanity detected such visitors. Oumuamua in 2017, 2I Borisov in 2019, and now this. Each visitor tells a different story. Oumuamua, that tumbling cigar-shaped wanderer, arrived with mysteries that persist to this day: its unusual acceleration, its lack of cometary activity, its strange reflectivity that sparked theories ranging from natural explanations to suggestions of alien technology. 2I Borisov behaved more like the comets we know, developing a proper tail and coma as it approached our sun, offering reassuring confirmation that some cosmic phenomena remain predictably beautiful. But 3I-ATLAS would prove to be something else entirely. The preliminary observations reveal an object of unusual size. Estimates suggest a nucleus potentially larger than Manhattan, dwarfing its interstellar predecessors. If confirmed, this would make it 100 times more massive than Oumuamua, 10 times larger than Borisov. Size matters in the cosmic realm, for larger objects carry more material, harbor more complex chemistry, and offer richer opportunities for scientific discovery. Yet size represents only the beginning of 3I-ATLAS's mysteries. As telescopes around the world turn their attention toward this visitor, each observation adds new pieces to an increasingly complex puzzle. The object shows signs of activity, the telltale fuzziness of outgassing that marks active comets. But the activity begins at distances where such behavior should be impossible, where the sun's warmth remains too weak to sublimate surface ices. The spectrographs, those instruments that decode the chemical signatures written in starlight, begin detecting emissions that challenge everything astronomers thought they understood about interstellar objects. The very atoms streaming from 3I-ATLAS's nucleus carry information about stellar environments, so alien, so removed from our solar system's experience, that they force scientists to reconsider fundamental assumptions about planetary formation and cosmic chemistry. Night after night, the observations accumulate. Each measurement brings new surprises, new challenges to conventional wisdom, new questions about the universe's capacity for wonder. The initial excitement of discovery transforms into something deeper, a growing realization that 3I-ATLAS represents more than just another interstellar visitor. It represents a revolution in our understanding of what exists in the spaces between stars. As July transitions into August, and August into September, 3I-ATLAS continues its relentless journey toward the Sunday. With each passing day, it grows brighter, more active, more revealing of its secrets. The astronomical community watches with mounting anticipation and puzzlement. Social media buzzes with speculation that ranges from sober scientific analysis to wild conspiracy theories about alien visitors and government cover-ups. But perhaps most remarkably, 3IATLAS forces us to confront a profound truth about our cosmic situation. We are not isolated. Our solar system exists within a galaxy where worlds routinely exchange material across interstellar distances, where the debris of ancient cataclysms wanders the void for billions of years, where chemistry that began around stars that died before Earth was born can arrive at our doorstep, carrying messages written in the universal language of physics. The night everything changed was July 1st, 2025. But the changes to our understanding, to our perspective, to our appreciation of the universe's interconnectedness would continue long after 3IATLAS disappeared behind the sun's glare and vanished once again into the cosmic deep. What secrets did this ancient wanderer carry? What stories did its chemistry tell about worlds and stars we could never hope to visit? The answers would challenge our assumptions, spark fierce debates, and ultimately remind us that the universe remains far stranger, far more wonderful than we dare imagine. The journey of discovery had only just begun. Picture, if you will, Manhattan Island, lifted from its foundation and set adrift in the cosmic ocean. Imagine this familiar landmass with all its towering skyscrapers, its millions of inhabitants, its bustling energy floating silently through the void, glowing green like some otherworldly beacon calling across the darkness. This is the scale of 3IATLAS, a wanderer stretching up to 5 6/10 kilometers across, 100 times more massive than Oumuamua, 10 times larger than Borisov. As it hurtles toward our sun at 137,000 miles per hour, a speed that would carry you from Earth to the Moon in less than 3 hours, something remarkable begins to happen. The ancient ice, dormant for eons in the interstellar cold, awakens to the growing warmth of our star. On July 21st, the Hubble Space Telescope captures this cosmic awakening with exquisite detail. Through Hubble's patient eye, we witness the birth of a coma, a teardrop-shaped cocoon of dust and gas streaming behind the nucleus like the train of some celestial wedding dress. This fuzzy envelope confirms what astronomers hope to see. 3IATLAS is indeed a comet, not merely a wandering asteroid, carrying within its frozen heart the water and organic compounds that speak to us of distant worlds. Yet even as this confirmation arrives, 3IATLAS refuses to conform to our expectations. Where familiar comets develop a single tail pointing away from the sun, swept back by the solar wind like hair in a cosmic breeze, this visitor does something unprecedented. It shoots a massive jet of material directly toward our star, a 6,000-mile cannon of gas and dust that defies every textbook diagram of cometary behavior. Imagine standing witness to this spectacle, this impossible fountain flowing not away from the sun, but toward it. The jet stretches across space with the majesty of a stellar waterfall, challenging our understanding of how comets should behave. Here is physics operating at the edge of our knowledge, revealing processes that no laboratory on Earth could replicate. The spectacle intensifies as summer progresses into autumn. Ground-based telescopes record the comet's steady brightening, their electronic eyes documenting each subtle change in luminosity as 3IATLAS responds to our sun's increasing influence. The coma expands like a slow-motion explosion, eventually stretching to twice Earth's diameter, a gossamer sphere of liberated molecules that could engulf our entire world. The green coloration that gives 3IATLAS its ethereal beauty comes from carbon-based compounds excited by solar radiation. These molecules, awakened from their billion-year slumber, dance with energy absorbed from our star's light. Each photon tells a story of chemistry that began in another stellar system, of carbon forged in the nuclear furnaces of alien suns, of organic complexity that survived the journey across interstellar space. But the true revelations await the application of our most sophisticated instruments. When the James Webb Space Telescope, that miracle of human engineering floating in the darkness beyond Earth's orbit, turns its infrared sensors toward 3 IAT-LAS on August 6th, it unveils a composition so extraordinary that it forces astronomers to question everything they thought they knew about interstellar objects. Consider the implications of what Webb discovers. Carbon dioxide dominates the outgassing at 87% by mass, creating chemical ratios 16 times higher than any comet previously observed in our solar system. This is not a subtle difference. This is a fundamental deviation from the cosmic chemistry we understand. Water vapor, the substance we associate most readily with comets, comprises only 4% of the STRI. Emissions, carbon monoxide fills most of the remainder, completing a chemical signature that speaks of formation conditions utterly alien to our cosmic neighborhood. In our solar system, comets form beyond the frost line, that invisible boundary where water ice can condense and remain stable. But 3 IAT-LAS apparently crystallized in an environment where carbon dioxide dominated conditions, requiring either temperatures so extreme or stellar radiation so unusual that our models struggle to accommodate them. The Spitzer Space Telescope archives, containing spectroscopic data from thousands of known comets, reveal no similar signatures. 3 IAT-LAS stands alone in astronomical records, unique among the cosmic wanderers we have studied. Yet even this extraordinary chemistry pales beside the discovery that would soon shake the astronomical community to its core. The Very Large Telescope in Chile's Atacama Desert, that installation where 8 mirrors work in perfect synchrony to create a light-gathering power equivalent to a telescope 50 meters across, detects something that should not exist in nature: atomic nickel vapor streaming from the nucleus, unaccompanied by ion emissions. Pause for a moment and consider what this means. Nickel and iron are cosmic siblings, forged together in stellar cores and rarely separated by natural processes. Their atomic structures ensure they almost always appear in combination, whether in terrestrial rocks, meteorites, or the cores of planets. To find nickel without iron is like discovering smoke without fire, effect without cause, a violation of the chemical relationships that govern matter throughout the universe. This discovery forces us to confront uncomfortable questions. What stellar environment could fractionate these elements so completely? What processes, unknown in our solar system's formation, could separate atomic species that nature herself seems determined to keep together? The very existence of this emission challenges our understanding of stellar nucleosynthesis, planetary formation, and the chemistry of cosmic evolution. Some researchers propose that 3 IAT-LAS originated from a planetary collision in a metal-rich system, where catastrophic violence separated elements in ways impossible under gentler circumstances. Others point toward formation around a carbon star, those rare stellar types that create atmospheric chemistry dominated by carbon compounds, rather than the oxygen-rich environments familiar in our cosmic neighborhood. Carbon stars were more common in the galaxy's youth, when stellar populations differed dramatically from today's stellar census. The polarimetric observations add yet another layer to this growing mystery. When astronomers examine the light reflected from 3 IAT-LAS's coma, they discover unusually high negative polarization light waves, oscillating predominantly along specific planes, rather than the random orientations typical of scattered starlight. This signature appears most commonly in trans-Neptunian objects, those distant denizens of our solar system's edge, where surfaces consist of mixed icy and dark organic material. But 3IATLAS formed not in the cold reaches of our solar system, but in the alien environment of another star's domain. Its polarization suggests a surface composition combining materials in proportions and our cosmic neighborhood never experienced ice and organics, mixed in ratios that speak of different temperature regimes, different radiation environments, different evolutionary pathways than those that shape the objects familiar to us. Each observation reveals 3IATLAS as a more complex, more extraordinary visitor than initial detection suggested. This is not simply an interstellar comet following predictable physics through our solar system. This is a museum piece from cosmic antiquity, a sample from stellar environments so alien that their very existence expands our conception of what is possible in the universe. The growing catalogue of anomalies creates a portrait of an object that challenges every assumption about interstellar visitors. Its size exceeds expectations. Its chemistry defies explanation. Its behavior contradicts textbook descriptions of cometary activity. Yet it remains demonstrably real, photographed by our finest instruments, analyzed by our most sophisticated spectrographs, tracked with mathematical precision as it follows the inexorable pull of gravitational physics toward its date with our Sunday. As autumn deepens and 3IATLAS continues its approach, each new observation adds detail to this portrait of impossibility. The comet becomes a cosmic laboratory, demonstrating chemistry and physics that no terrestrial experiment could replicate. Its very existence proves that the universe harbors processes, environments, and evolutionary pathways far beyond the narrow range of conditions that produced our solar system. Here, carried to our doorstep by the patient mechanics of orbital motion, is direct evidence of cosmic diversity. The galaxy contains stellar systems so different from our own that their refuse challenges our fundamental understanding of planetary formation. Their chemistry operates according to physical laws we recognize, but under conditions so extreme that the results seem almost supernatural. 3IATLAS forces us to expand our definition of what is possible. It demonstrates that the universe's capacity for surprise exceeds even our most imaginative theories. In its green glow and impossible chemistry, we glimpse the true diversity of cosmic evolution, a reminder that our solar system represents just one example of planetary formation among countless variations played out across the galaxy's vast expanse. The anatomy of the impossible reveals itself as simply the anatomy of the previously unknown. 3IATLAS carries within its frozen nucleus the proof that the universe remains far stranger, far more wonderful than we have yet dared to imagine. Deep within the frozen nucleus of 3IATLAS, locked in crystalline ice that has remained undisturbed for billions of years, lies a library of cosmic history that no human archive could match. Each molecule carries within its atomic structure the story of conditions in a distant star system, when our own sun existed only as a vast cloud of gas and dust, slowly collapsing under its own gravity. The chemistry emerging from this interstellar wanderer as it awakens to our sun's warmth forces scientists to confront the most fundamental question in planetary science: just how diverse can the universe become? The carbon dioxide abundance that dominates 3IATLAS's emissions, it represents more than a simple chemical curiosity. It constitutes a revolutionary challenge to our understanding of planetary formation itself. In our solar system, comets crystallize beyond the frost line, that invisible boundary where temperatures drop sufficiently for water ice to condense and remain stable. Here, water dominates the chemistry of accretion, creating the familiar icy bodies that populate the Kuiper Belt and Oort cloud. But 3IATLAS apparently formed in an environment where carbon dioxide, not water, provided the primary condensable ice. This requires conditions so alien to our experience that theoretical models struggle to accommodate them. Perhaps the comet originated around a star with such unusual luminosity that carbon dioxide remained the dominant ice species. Perhaps it formed in the aftermath of stellar evolution processes that heated the system sufficiently to drive off water while preserving more refractory compounds. The Spitzer Space Telescope archives, containing detailed spectroscopic observations of thousands of comets across decades of operation, reveal the true magnitude of this anomaly. Among all the known comets in our cosmic census, objects spanning the full range of orbital parameters, formation, locations, and evolutionary histories, none approach the carbon dioxide ratios observed in 3 IATLAS. This visitor stands absolutely alone in astronomical records, a chemical signature without precedent in our accumulated knowledge of the solar system. When water detection finally arrives on July 20th through near-infrared spectroscopy at Gemini South and NASA's Infrared Telescope facility, even this seemingly normal discovery carries profound surprises. The Swift Observatory's ultraviolet observations on July 30th and August first detect hydroxyl ions, the molecular fragments that result when solar radiation tears water molecules apart with photonic violence. But this process begins when 3 IATLAS sits nearly 3 times Earth's distance from the Sun, where solar heating should remain insufficient to drive such vigorous molecular dissociation. Consider the implications. This is water outgassing occurring under conditions where conventional physics suggests it should be impossible. The mechanism behind this premature activity becomes clear only through detailed laboratory analysis of the spectroscopic data. Rather than surface ice, sublimating directly from solid to gas, the familiar process that creates cometary activity in our solar system, 3 IATLAS, appears to be releasing microscopic ice-coated dust grains that carry frozen materials far from the nucleus before vaporizing in the weak solar wind. This process represents a fundamentally different mode of cometary evolution. Instead of surface sublimation gradually eroding the nucleus, 3 IATLAS employs a delivery system that transports volatile materials through space before releasing them in locations where conventional thermodynamics would predict stability. The comet has essentially evolved its own mechanism for remaining active at distances where familiar physics would render it dormant. But if the water emissions challenged conventional understanding, the discovery that arrives on August 8th shatters it entirely. The detection of atomic nickel vapor streaming from the nucleus, unaccompanied by ion emissions, represents a violation of cosmic chemistry so fundamental that it forces researchers to question whether they understand stellar nucleosynthesis at all. In the heart of every star, nuclear fusion creates the elements that comprise planets, asteroids, and comets. The process follows well-established patterns. Hydrogen fuses to helium, helium burns to carbon and oxygen, and in the most massive stars, silicon burning creates iron peak elements including nickel and iron. These elements form together, exist together, and disperse together when stellar explosions scatter them across interstellar space. To find nickel without iron is to discover an effect without its cause, a cosmic chemistry that violates the fundamental processes of stellar evolution. Some researchers propose that 3 IATLAS originated from a planetary collision in a system with unusual metallicity, perhaps a world where extreme differentiation had concentrated nickel-rich materials in specific locations that could be selectively ejected during catastrophic impact. Others point toward formation around a carbon star, those rare stellar types that create atmospheric chemistry dominated by carbon compounds rather than the oxygen-rich environments familiar in our cosmic neighborhood. Carbon stars represent a brief phase in stellar evolution when nuclear burning processes temporarily invert normal atmospheric chemistry. Instead of oxygen-dominated compounds, these stars create environments rich in carbon monoxide, carbon dioxide, and complex organic molecules. If 3IATLAS formed in such a system, its exotic chemistry might reflect stellar nucleosynthesis operating under conditions that our Sun, a relatively ordinary star by galactic standards, never experienced. The isotopic signatures, when they become available through high-resolution spectroscopy, may ultimately provide the most definitive answers. Different stellar environments create distinct ratios of atomic isotopes, subtle variations in nuclear structure that serve as cosmic fingerprints for the conditions under which elements formed. 3IATLAS carries these chemical signatures from its birth system, potentially allowing scientists to reconstruct not merely when it formed, but the specific stellar environment that created its parent materials. The polarimetric observations conducted throughout July and August add yet another dimension to this chemical mystery. When the Very Large Telescope, Nordic Optical Telescope, and Rosen Observatory examine the light scattered from 3IATLAS's coma, they discover polarization characteristics unlike any previously observed in interstellar objects. The high degree of negative polarization, light waves preferentially oriented along specific planes, typically appears only in trans-Neptunian objects with surfaces of mixed icy and organic composition. But 3IATLAS formed not in our solar system's cold outer reaches, but in the alien environment of another star's planetary zone. Its polarization suggests surface materials combined in proportions never achieved in our cosmic neighborhood, perhaps reflecting formation temperatures, pressure regimes, or radiation environments so different from local conditions that they produced entirely novel material properties. Each new observation reinforces the conclusion that 3IATLAS represents more than an unusual visitor. It constitutes living proof of cosmic diversity that exceeds our most imaginative theories. The chemistry emerging from its nucleus demonstrates that stellar systems can evolve along pathways so divergent from our own experience that their products challenge fundamental assumptions about planetary formation. This is not simply a matter of different initial conditions producing predictable variations. The chemistry of 3IATLAS suggests evolutionary processes operating according to physical principles we recognize, but under environmental constraints so extreme that the results appear almost supernatural. The nickel emissions without iron, the carbon dioxide-dominated ices, the premature water outgassing, the exotic polarization signatures. Each anomaly points toward formation conditions that stretch the boundaries of what we considered possible. The implications extend far beyond a single interstellar visitor. If 3IATLAS represents material from the galaxy's ancient past formed when stellar populations, galactic chemistry, and planetary formation processes differed dramatically from current conditions, then it provides our first direct sample of cosmic evolution operating under constraints that no longer exist anywhere in the observable universe. Consider what this means for our understanding of life's potential distribution throughout the galaxy. If stellar systems can produce chemistry this exotic, this removed from our experience, how much greater might be the diversity of environments capable of supporting biological evolution? 3IATLAS reminds us that our solar system, with its familiar chemistry, predictable planetary arrangement, and stable stellar environment, may represent just one narrow example among countless variations of cosmic evolution. The textbooks will indeed require rewriting. The chemical principles we thought universal proved to be merely local. The formation processes we considered fundamental reveal themselves as contingent upon environmental conditions that may be far rarer than we assumed. 3IATLAS carries within its ancient nucleus the humbling reminder that the universe's capacity for surprise extends far beyond our current theories. In its impossible chemistry, we glimpse the true scope of cosmic creativity, a universe capable of evolutionary experiments so bold, so removed from our expectations, that their very existence expands our definition of what nature can achieve. The library of cosmic history contained within 3IATLAS remains largely unread, its volumes written in the universal language of atomic structure and molecular bonds. But what we have deciphered so far suggests that the universe's stories far exceed even our most ambitious imaginings. In the normally measured world of peer-reviewed astronomy, where discoveries unfold through careful observation and methodical analysis, the scientific investigation of 3IATLAS transforms into something resembling a cosmic detective story, complete with conflicting theories, heated exchanges, and accusations flying across academic journals like bullets in a scholarly gunfight. At the center of this extraordinary controversy stands a figure who has become astronomy's most provocative voice. Avi Loeb, Harvard's former astronomy department chair, whose bold suggestion that this visitor might represent alien technology ignites a firestorm that spreads far beyond the confines of academic circles. The story begins on July 16th, with the publication of a paper that reads more like a criminal indictment than a typical astronomical study. Loeb, working with researchers from the Initiative for Interstellar Studies, presents what he terms the case against 3IATLAS being a natural object. Like a prosecutor laying out evidence before a jury, he catalogues 7 distinct anomalies that, when considered together, challenge every natural explanation for this visitor's characteristics. The orbital alignment provides the most statistically compelling argument. 3IATLAS approaches our solar system along a trajectory that places it remarkably close to the ecliptic plane, the flat disk that contains Earth's orbit and most planetary motion. For a truly random interstellar object, such alignment carries a probability of only 1 in 500. Imagine flipping a coin and achieving heads 10 times in succession. The mathematics, too of chance, makes such coincidences possible, but profoundly unlikely. Loeb argues that this trajectory suggests intent rather than accident, planning rather than chance. He references Liu Cixin's science fiction concept of the dark forest, the idea that alien civilizations might act preemptively to eliminate potential threats posed by emerging technological species. In this scenario, 3IATLAS represents not a wandering comet, but a reconnaissance probe, perhaps even a weapon system, dispatched by a civilization that views humanity's rapid technological development with alarm. The astronomical community responds with unusual intensity and barely concealed frustration. Chris Lintott, a respected researcher known for measured responses to controversial claims, immediately criticizes the speculation as premature and scientifically irresponsible. Other mainstream astronomers express disappointment that sensational theories receive public attention, while legitimate research proceeds without fanfare. Life Science reports an overwhelming consensus that 3IATLAS represents a natural comet, with many researchers arguing that extraordinary claims require extraordinary evidence that simply does not yet exist. But Loeb refuses to retreat from his position. In subsequent blog posts and media interviews, he doubles down on the artificial origin hypothesis, assigning a 30 to 40% probability that 3IATLAS does not have a fully natural origin. His August 23rd analysis argues that the nickel without iron emission signature resembles industrially manufactured alloys more than products of natural stellar nucleosynthesis. He calculates that if 3IATLAS exceeds 5 kilometers in diameter, as some size estimates suggest, then natural explanations become what he terms untenable, given the extreme rarity of such large interstellar objects. The debate intensifies dramatically when citizen astronomers begin claiming detection of rhythmic Doppler shifts in radio emissions from 3IATLAS. These amateur researchers, working with modest equipment but unlimited enthusiasm, report finding patterns in the radio data that suggest encoded communication, artificial signals hidden within natural emissions, like messages concealed in cosmic static. If confirmed, such discoveries would transform the debate from academic speculation into the most significant scientific revelation in human history. The SETI Institute responds by deploying the Allen Telescope Array, that sophisticated network of radio dishes designed specifically for detecting extraterrestrial intelligence. Beginning on July 2nd, the array conducts the most intensive radio search ever focused on a single astronomical target, accumulating 21 terabytes of data within the first week. This represents computational analysis equivalent to thousands of hours of high-definition video, each bit examined for traces of artificial structure that might indicate technological origin. Initial analysis reveals no confirmed artificial signals, but the search continues with methodical determination. As 3IAT LAS approaches its closest encounter with our Sunday, the radio astronomers understand that they are hunting for needles in haystacks, seeking patterns so subtle they might be indistinguishable from noise, yet so significant they could rewrite humanity's understanding of its place in the universe. Meanwhile, social media amplifies the controversy with viral intensity that transforms academic debate into global spectacle. Posts falsely attributing quotes to renowned physicist Michio Kaku spread across platforms, claiming the object approaches Earth with hostile intent and reconnaissance capabilities that sound more like science fiction than scientific analysis. The hashtag 3IATLAS trends internationally as users debate everything from government cover-ups to imminent alien contact, creating an information ecosystem where speculation often drowns out legitimate scientific analysis. The viral nature of these theories reveals something profound about human psychology and our relationship with cosmic discovery. Faced with genuine mystery, an object whose properties challenge conventional understanding, the public imagination leaps immediately to the most extraordinary possible explanations. The idea that we might be witnessing humanity's first contact with alien technology proves irresistibly compelling, even without supporting evidence. Conspiracy theories proliferate with digital speed, each iteration adding new layers of speculation about government secrecy, military responses, and hidden preparations for alien encounter. Some posts claim that 3IATLAS represents advanced reconnaissance for a larger alien force. Others suggest it carries technology that could revolutionize human civilization or destroy it entirely. The boundary between legitimate scientific speculation and wild imagination blurs until rational discourse becomes nearly impossible. Yet beneath this digital cacophony, legitimate researchers work with quiet determination to test each claimed anomaly through rigorous scientific method. Statistical analysis by respected astronomers Scott Manley and David Kipping reveals significant flaws in Loeb's trajectory calculations, demonstrating that the orbital alignment may be far less remarkable than initial estimates suggested. Their work exemplifies the self-correcting nature of science, showing how peer review and independent analysis gradually separate signal from noise. Ehsanul Haq, a researcher at the SETI Institute, publishes perhaps the most comprehensive response to the alien technology hypothesis. His detailed analysis, appearing on the Earth, our EXIV preprint server, systematically addresses each anomaly cited by Loeb's team. Haq demonstrates that 3IATLAS exhibits behavior entirely consistent with known interstellar objects when analyzed using appropriate statistical methods and comparative frameworks. The orbital alignment, Haq argues, appears remarkable only when considered in isolation. When placed in the context of galactic dynamics and the preferential directions from which interstellar objects approach our solar system, such trajectories prove far more common than initial estimates suggested. The chemical anomalies, while unusual, fall within the range of compositions expected for objects formed in the diverse stellar environments that populate our galaxy's history. NASA's Tom Statler, the agency's lead scientist for solar system small bodies, provides perhaps the most succinct assessment of the controversy. It very, very strongly resembles, in just about every way, the comets that we know. It has some interesting properties that are a little bit different from our solar system comets, but it behaves like a comet. The evidence is overwhelmingly pointing to this object being a natural body. Yet the debate reveals something important about the nature of scientific discovery in our connected age. The rapid global spread of theories about 3IATLAS, from legitimate scientific speculation to wild conspiracy theories, demonstrates how the public hunger for cosmic revelation remains as strong as ever. Each potential breakthrough becomes an event that captures international imagination, inspiring both serious scientific inquiry and creative flights of fancy that stretch far beyond available evidence. The controversy also highlights the challenge of conducting science under intense public scrutiny. Traditional peer review processes, designed for methodical evaluation of evidence over months or years, struggle to keep pace with social media speculation that evolves in real time. Scientists find themselves defending preliminary findings against premature conclusions, while simultaneously trying to maintain public interest in legitimate research that proceeds at the careful pace necessary for reliable results. Perhaps most significantly, the 3IATLAS debate illustrates how extraordinary discoveries inevitably challenge the boundaries between known and unknown, possible and impossible, natural and artificial. When confronted with phenomena that stretch the limits of current understanding, even trained scientists may find themselves considering explanations that would seem ridiculous under normal circumstances. The cosmic detective story continues as 3IATLAS approaches its date with our Sun, each new observation adding evidence to arguments on both sides of the debate. Whether this visitor represents natural cosmic evolution operating under extreme conditions or something far more extraordinary remains an open question that may not be resolved until long after the object disappears once again into interstellar space. But perhaps the most important discovery emerging from this controversy lies not in 3IATLAS itself, but in what it reveals about humanity's relationship with cosmic mystery. Faced with genuine wonder, with phenomena that challenge our understanding of what is possible, we reveal ourselves as a species still capable of awe, still hungry for revelation, still willing to consider that the universe might harbor surprises that exceed even our most ambitious imaginings. The detective story of 3IATLAS reminds us that science, at its best, remains an adventure of discovery, where the most important questions often prove to be those we never thought to ask. 7 billion years ago, when our solar system existed only as a diffuse cloud of gas and dust slowly condensing under the patient pull of gravity, 3IATLAS was already ancient beyond measure. Imagine, if you can, the sweep of cosmic time that this implies. When the first stirrings of planetary formation began around our young sun, this visitor had already been wandering the galaxy for eons, carrying within its frozen heart the chemical signatures of stellar environments that existed before Earth itself was even a possibility. If spectroscopic analysis proves correct about its origins in the Milky Way's thick disk, 3IATLAS represents something far more extraordinary than merely an unusual comet. It constitutes a time capsule from the galaxy's earliest epoch of planet formation, a messenger carrying secrets about cosmic conditions that no longer exist anywhere in the observable universe. To study this object is to examine direct samples from an era of galactic evolution that we can normally investigate only through the faintest, most distant starlight. The thick disk formation era that preceded our solar system's birth by billions of years represents a cosmic environment so alien to our experience that theoretical models struggle to capture its essential character. Stars in this ancient galactic region condensed from primordial gas clouds, with radically different compositions than the enriched material that eventually gave birth to our Sun and planets. Heavy elements, the metals that astronomers call everything heavier than hydrogen and helium, remained scarce, existing in abundances barely 1/10 of current galactic standards. Picture a galaxy where stellar nurseries operated according to different rules, where the absence of heavy elements created stars with unusual masses, luminosities, and evolutionary pathways. The radiation environments around these ancient stars differ dramatically from anything we observe today. Planetary formation, when it occurred at all, proceeded under constraints that produced worlds unlike any in our cosmic neighborhood. The very chemistry of accretion operated with elemental abundances so skewed toward primordial simplicity that the resulting objects would seem alien even to astronomers familiar with the full diversity of our solar system. 3 IATLAS potentially originated during this ancient epoch, making it older than 99% of all known objects in our rooms. Cosmic census. Consider what this means. The minerals locked within its nucleus crystallized from stellar materials when the galaxy itself was young, when the processes of cosmic evolution had barely begun. The slow work of enriching interstellar space with the heavy elements that make possible both rocky planets and biological complexity. Galactic archaeology, that sophisticated field that traces cosmic evolution through the motion and chemistry of stellar populations, allows astronomers to reconstruct 3 IATLAS's likely journey through space and time. By analyzing its current trajectory and velocity, researchers can calculate backward through billions of years of galactic rotation, tidal forces, and gravitational encounters to determine possible source regions and formation scenarios. The object's hyperbolic excess velocity of 58 kilometers per second, significantly faster than either Oumuamua or Borisov, provides crucial evidence about its origins. This speed suggests formation either much closer to the galactic center, where gravitational interactions routinely accelerate objects to extreme velocities, or origins in a completely different stellar population than previous interstellar visitors. The velocity signature points toward birth in environments where the normal rules of planetary formation operated under such extreme conditions that the results challenge our understanding of what cosmic evolution can achieve. The chemical composition emerging from spectroscopic analysis provides additional clues about ancient star formation processes that operated according to principles we can barely reconstruct. The extreme carbon dioxide abundance suggests condensation around a carbon star, those rare stellar types that create atmospheric chemistry, dominated by carbon compounds, rather than the oxygen-rich environments familiar throughout our cosmic neighborhood. Carbon stars represent a brief but dramatic phase in stellar evolution when nuclear burning processes temporarily invert normal atmospheric chemistry. Instead of oxygen-dominated compounds like water and silicates, these stars create environments rich in carbon monoxide, carbon dioxide, and complex organic molecules that polymerize into long-chain hydrocarbons of startling complexity. If 3 IATLAS formed in such a system, its exotic chemistry might reflect stellar nucleosynthesis, operating under conditions that our Sun, a relatively ordinary star by galactic standards, never experienced and never will experience. Such stellar environments were far more common in the galaxy's youth, when stellar populations consisted primarily of massive, short-lived stars that evolved rapidly through their nuclear burning phases. These ancient giants created and dispersed heavy elements at rates that exceeded the galaxy's current stellar recycling processes, but they also produced radiation environments and chemical abundances that have no modern analogues. The isotopic signatures that will eventually emerge from high-resolution spectroscopic analysis may provide the most definitive evidence of 3 IATLAS's extreme antiquity. Different stellar environments create characteristic ratios of atomic isotopes, subtle variations in nuclear structure that serve as cosmic fingerprints for the specific conditions under which elements formed. These signatures remain preserved in solid materials for billions of years, creating an indelible record of stellar nucleosynthesis that no subsequent processing can entirely erase. 3-IATLAS carries these chemical fingerprints from its birth system like a cosmic birth certificate, potentially allowing scientists to reconstruct not merely when it formed, but the detailed stellar environment that created its constituent materials. If the isotopic ratios confirm formation around ancient metal-poor stars, they will provide unprecedented insight into galactic chemical evolution during epochs we can normally study only through the most distant, faintest astronomical observations. But the implications extend far beyond the biography of a single comet. If 3-IATLAS truly represents material from the galaxy's thick disk, it constitutes our first direct sample of stellar environments that operated under fundamentally different constraints than those familiar today. Previous studies of galactic evolution relied entirely on distant observations of ancient stars and sophisticated theoretical models of early stellar nucleosynthesis. This visitor brings laboratory samples directly to our instruments, enabling precision analysis that would be impossible through any other means. Understanding 3-IATLAS helps illuminate the broader question of how planetary systems evolve over cosmic timescales that dwarf human history. Early stellar environments likely produced entirely different classes of planets, asteroids, and comets than the objects familiar throughout our solar system. The extreme chemical compositions, unusual isotopic signatures, and exotic mineralogy that characterize ancient stellar systems might have created worlds so alien to our experience that they would seem like alien artifacts, even to astronomers familiar with the full diversity of exoplanetary systems. By studying this ancient survivor, researchers gain insights into the fundamental question of cosmic diversity. Just how varied can planetary formation become when operating under different environmental constraints? The answer emerging from 3-IATLAS suggests that the universe's capacity for creating unusual worlds far exceeds even our most imaginative theoretical models. Consider the implications for our understanding of life's potential distribution throughout the galaxy. If stellar systems can produce chemistry as exotic as that displayed by 3-IATLAS compositions, so removed from our experience that they challenge basic assumptions about planetary formation, how much greater might be the first diversity of environments capable of supporting biological evolution? This visitor reminds us that our solar system, with its familiar chemistry and predictable planetary architecture, may represent just one narrow example among countless variations of cosmic evolution. The organic compounds detected in 3-IATLAS's coma provide particularly intriguing evidence of this diversity. These carbon-based molecules, synthesized in stellar environments billions of years ago, have survived interstellar transit that would destroy most complex chemistry. Their persistence suggests that organic complexity, the foundation of biological systems, can emerge and endure under conditions far more extreme than those that prevailed during Earth's formation. The polarimetric signatures that distinguish 3-IATLAS from familiar comets point towards surface compositions that reflect formation under temperature, pressure, and radiation regimes unlike anything experienced in our cosmic neighborhood. These exotic material properties suggest evolutionary pathways that operated according to physical principles we recognize, but under environmental constraints so alien that the results appear almost supernatural. 3-IATLAS forces us to confront the humbling reality that our solar system, with its orderly planetary arrangement, stable stellar environment, and familiar chemical compositions, may be far more unusual than we have assumed. The cosmic evolution that produced Earth and its neighboring worlds proceeded under conditions that may prove to be rare exceptions rather than typical examples of planetary formation. In this ancient visitor, we glimpse the true scope of cosmic creativity, a universe capable of evolutionary experiments so bold, so removed from our local experience, that their very existence expands our definition of what nature can achieve. The messages from the deep past carried within 3 IATLAS remind us that the galaxy has been conducting vast experiments in world building for billions of years, most of which remain entirely unknown to us. As 3 IATLAS continues its journey toward our Sun, it carries with it the accumulated wisdom of cosmic evolution, operating under constraints that no longer exist anywhere in the observable universe. In its impossible chemistry and ancient mineralogy, we find direct evidence that the universe's stories exceed even our most ambitious attempts at imagination. The deep past speaks to us through this wandering archive, whispering of worlds and stars that died before our own cosmic neighborhood began its slow dance around the galactic center. These are messages written in the universal language of atomic structure and molecular bonds, waiting to be decoded by minds capable of appreciating their profound significance. The discovery of 3 IATLAS triggers what becomes the most ambitious astronomical observation campaign ever coordinated for a single celestial target. Within hours of confirming its interstellar nature, observatories scattered across our planet begin a carefully choreographed dance of data collection that pushes the very boundaries of human technological capability. This is no ordinary scientific investigation. This is a race against the cosmos itself, with time measured not in human convenience but in the inexorable mechanics of orbital motion. The challenge seems almost insurmountable from the very beginning. Ground-based telescopes, designed for the patient observation of stationary stars and galaxies, must suddenly track an object moving at interstellar speeds while maintaining the precise focus and calibration necessary for spectroscopic analysis. Imagine trying to photograph a racing hummingbird from a moving car while simultaneously adjusting your camera settings to capture details invisible to the naked eye. The comet's path carries it through different regions of the sky each night, requiring constant adjustment of pointing systems that were never designed for such dynamic tracking. Atmospheric turbulence, weather patterns, and the simple rotation of our planet all conspire against continuous observation. Earth-based astronomy operates at the mercy of atmospheric conditions that can transform the most sophisticated telescope into little more than an expensive paperweight when clouds roll across the sky. Yet the international community of astronomers understands that this opportunity may never come again, at least not in any of our lifetimes. Space-based observatories provide the most stable viewing platforms, but they bring their own unique limitations and challenges. The Hubble Space Telescope, that venerable workhorse of space astronomy, can indeed track moving targets with remarkable precision, but its observations must be scheduled weeks in advance through a complex allocation process that weighs competing scientific priorities. Every minute of Hubble's time represents a precious resource that astronomers around the world compete to access. The James Webb Space Telescope offers unprecedented sensitivity and spectroscopic capability, but its complex mirror system and sophisticated instruments require extreme precision in tracking calculations. A single error in trajectory prediction could point these magnificent instruments toward empty space, wasting observational opportunities that might not be replaceable. The stakes could hardly be higher. Webb's infrared vision can reveal chemical compositions invisible to ground-based telescopes, but only if its targeting systems can maintain lock on an object following a hyperbolic trajectory through the solar system. The breakthrough in this cosmic chase comes through international coordination of unprecedented scope and sophistication. When 3 IATLAS passes close to Mars on October 3rd, European Space Agency orbiters provide a unique observational opportunity that transforms the red planet from a distant world into a strategic observatory. The Trace Gas, Orbiter's CARSIS camera, designed to photograph Martian terrain from an altitude of just a few hundred kilometers, attempts something it was never intended to do: capture images of an interstellar visitor 30 million kilometers away. Consider the audacity of this endeavor. The CARSIS camera normally photographs geological features on Mars's surface: rocks, craters, and dust formations that reflect bright sunlight from distances measured in hundreds of kilometers. Now it must detect 3 IATLAS, an object 100,000 times fainter than its usual targets, against the black backdrop of interstellar space. The technical challenge resembles trying to photograph a candle flame from across an entire continent while distinguishing it from the surrounding darkness. Yet the 5-second exposures succeed beyond all expectations, revealing the fuzzy white dot of 3 IATLAS's coma as it maintains cometary activity even at Mars's distance from the Sunday. These images provide crucial confirmation that the visitor remains active far beyond the distances where conventional comets typically become dormant. Each pixel in these photographs represents a triumph of engineering precision and international scientific cooperation. NASA's planetary missions throughout the solar system join this coordinated effort with enthusiasm that transcends normal mission parameters. The Perseverance rover, designed to search for signs of ancient life on Mars, attempts observations from the planet's surface using instruments never intended for astronomical purposes. Multiple spacecraft scattered across the solar system turn their cameras and spectrographs toward this unprecedented visitor, creating an impromptu network of observatories spanning distances measured in astronomical units. Even Jupiter-bound missions like ESA's JUICE prepare for potential encounters as 3 IATLAS continues its journey through the outer solar system. Mission planners work feverishly to determine whether spacecraft trajectories might provide additional observational opportunities during the comet's outbound journey. Each possible encounter represents a chance to gather data that could answer fundamental questions about interstellar chemistry and cosmic evolution. The technical achievements that emerge from this campaign border on the miraculous. Imaging something smaller than Manhattan from distances of hundreds of millions of kilometers requires precision equivalent to photographing a mobile phone on the moon's surface from Earth while accounting for the phone's motion across the lunar landscape. Advanced adaptive optics systems work in real time to correct for atmospheric distortion, their computerized mirrors adjusting hundreds of times per second to compensate for the turbulent air that blurs astronomical images. Space telescopes execute complex pointing maneuvers that would have been impossible just decades ago, their attitude control systems maintaining target lock while following 3 IATLAS's hyperbolic trajectory through space. The mathematical precision required for these observations represents a triumph of celestial mechanics, the calculations that must account for the gravitational influences of every major body in the solar system. Radio astronomy adds another crucial dimension to this international campaign. The Allen Telescope Array, that sophisticated network of radio dishes designed specifically for searching for extraterrestrial intelligence, conducts the most intensive SETI observation ever focused on a single astronomical target. The array monitors both narrowband emissions that might indicate artificial signals and natural radio signatures from molecular transitions that reveal chemical composition and physical conditions within the comet's coma. The 21 terabytes of data collected during the first week of radio observations represents computational analysis equivalent to processing thousands of hours of high-definition video. Every byte must be examined for patterns that might indicate artificial structure, for frequencies that match no known natural process, for modulations that could carry encoded information from distant civilizations. The analysis requires supercomputer resources and signal processing algorithms that push the boundaries of current technology. As 3 IATLAS approaches solar conjunction on October 21st, the observational window begins to close with astronomical inevitability. Earth-based telescopes gradually lose their race against celestial mechanics as the comet moves closer to the Sun's position in our sky, eventually disappearing entirely behind our star's overwhelming glare. For several weeks, no direct observations become possible, a frustrating blackout period when the most interesting cometary activity might be occurring at perihelion passage. This blackout represents one of astronomy's fundamental limitations. Our Earth-bound perspective restricts us to observing only those portions of the solar system that happen to be visible from our particular location at any given time. Solar conjunction events render objects temporarily invisible regardless of our technological sophistication, forcing astronomers to accept gaps in their observational coverage that no amount of international cooperation can overcome. Yet the coordination extends far beyond professional astronomy to encompass a global community of citizen scientists whose contributions prove invaluable to the overall effort. Amateur observers worldwide contribute crucial data, particularly during the early weeks following discovery when professional telescopes were still being programmed for tracking procedures. These dedicated individuals, working with modest equipment but unlimited enthusiasm, maintain continuous monitoring that supplements official observations and fills gaps in professional coverage. Citizen scientists process vast quantities of image data, hunt through archival surveys for pre-discovery observations, and provide real-time tracking updates that help professional observatories maintain accurate pointing. Their contributions demonstrate that significant astronomical research no longer requires access to the world's largest telescopes. Dedication and skill can produce scientifically valuable results using equipment available to serious, amateur astronomers. The coordination protocols developed for observing 3 IATLAS establish new standards for international scientific cooperation that will undoubtedly influence future astronomical campaigns. The rapid sharing of observational data, the coordination of telescope schedules across multiple time zones, and the integration of amateur and professional observations create a template for studying future interstellar visitors with maximum efficiency and scientific return. This great cosmic chase reveals humanity at its collaborative best, international teams working with single-minded determination to extract every possible bit of information from a fleeting opportunity that spans mere months in cosmic time. The technical achievements, the international cooperation, and the sheer audacity of attempting to study an object from another star system demonstrate our species' remarkable capacity for curiosity-driven exploration. As 3 IATLAS vanishes behind the Sun's glare, the data analysis phase begins months or years of careful study that will extract scientific insights from every pixel of imagery, every line of spectroscopic data, every terabyte of radio observations. The chase may be ending, but the discovery process continues, promising revelations that will enhance our understanding of cosmic evolution for decades to come. The universe delivered this extraordinary visitor to our cosmic doorstep with surgical precision, and humanity responded with a coordinated effort that demonstrates our growing capability to study phenomena that would have remained entirely invisible to previous generations. In this great chase across the solar system, we glimpse our potential for future exploration of cosmic mysteries that await discovery in the darkness between stars. 3 IATLAS vanishes behind the Sun on October 21, 2025, disappearing into the solar glare like a cosmic magician's final act. But its impact on human understanding reverberates far beyond that moment of celestial conjunction, creating ripples of discovery that will continue expanding long after the visitor itself returns to the darkness between stars. This single wanderer has fundamentally altered how we perceive our place in the galaxy and our capacity to study distant worlds through the messengers they send to our cosmic doorstep. The immediate scientific legacy reshapes multiple fields of astronomical research with the force of revelation. Planetary formation models, built over decades of careful observation and theoretical refinement, must now accommodate environments that produce carbon dioxide-dominated ices and metal distributions so exotic they challenge basic assumptions about stellar nucleosynthesis. The textbooks that graduate students study will require fundamental revision, their chapters on cometary chemistry expanded to include possibilities that seemed impossible just months before. Galactic evolution theories gain new constraints from direct chemical analysis of material that originated in stellar environments billions of years older than our solar system. For the first time, astronomers possess laboratory samples, actual atomic evidence of cosmic processes that operated under conditions no longer existing anywhere in the observable universe. This transforms galactic archaeology from a discipline based on distant observations and theoretical models into one grounded in direct chemical analysis of ancient stellar products. Even astrobiology benefits from 3 IATLAS's revelations, as the discovery demonstrates, conclusively that organic compounds and complex chemistry can survive billion-year journeys through the radiation-bathed vacuum of interstellar space. The implications for panspermia, the hypothesis that life might spread between worlds carried by exactly such wandering objects, gain new credibility from evidence that even delicate molecular structures can endure cosmic voyages that span galactic distances. But the true revolution lies not in what 3 IATLAS has taught us, but in what it represents for the future of cosmic discovery. The Vera Rubin Observatory, beginning full operations in late 2025, will detect dozens of similar visitors each year through systematic surveys of unprecedented sensitivity and scope. Current projections suggest that hundreds of interstellar objects await discovery in the coming decade, transforming these encounters from rare, once-in-a-lifetime events into routine observations that provide continuous sampling of distant star systems. Consider what this means. Within a few years, astronomers will possess chemical samples from dozens of different stellar environments, each carrying its own story of planetary formation under alien conditions. Some may originate from young stellar systems where planet formation remains actively occurring, bringing fresh samples of protoplanetary disk material that reveal ongoing world-building processes. Others might represent fragments from catastrophic planetary collisions, offering direct analysis of exoplanet compositions that we could never hope to study through conventional astronomical observation. The diversity of these cosmic messengers will reveal patterns in galactic chemistry, stellar evolution, and planetary system architecture that remain entirely invisible through traditional telescope-based research. Each visitor carries within its nucleus a sample return mission that traveled billions of years to reach our instruments, delivering scientific data that no human spacecraft could possibly collect within reasonable timeframes. The technological implications extend far beyond passive observation into the realm of active interstellar exploration. Mission concepts for intercepting future visitors are already under development by space agencies worldwide, recognizing that systematic surveys will provide years of advance warning for the most scientifically valuable targets. Unlike 3 IATLAS, which arrived with insufficient notice for spacecraft deployment, future interstellar objects will be tracked from the moment they enter the outer solar system. Rapid response missions could deliver close-up analysis capabilities that dwarf anything possible through ground-based observation. Imagine spacecraft that rendezvous with interstellar visitors, deploying landers to sample their surfaces directly, or maintaining escort formations that provide continuous monitoring throughout their solar system passage. The scientific return from such missions would exceed anything achievable through remote observation, potentially answering fundamental questions about cosmic evolution that have puzzled astronomers for generations. Sample return missions represent the ultimate prize, actually bringing pieces of other star systems back to Earth for analysis in terrestrial laboratories, equipped with instruments far more sophisticated than anything that can be deployed in space. The technical challenges are formidable. Matching velocities with objects traveling at interstellar speeds requires propulsion capabilities that stretch current technological limits. But the scientific rewards justify even the most ambitious engineering efforts. The discovery process itself demonstrates humanity's rapidly growing capability to monitor our cosmic environment with sensitivity that approaches comprehensive awareness. The ATLAS system that found 3I-ATLAS represents just one component of an expanding network of sky surveys that will soon provide near real-time knowledge of everything moving through the solar system larger than a few meters in diameter. This capability has implications that extend far beyond pure astronomy into realms of planetary defense and space situational awareness. The same technologies that detect interstellar visitors also identify potentially hazardous asteroids years before they might pose threats to Earth. The global network of detection systems creates an early warning capability that transforms asteroid impact from an unpredictable natural disaster into a manageable engineering challenge. Perhaps most significantly, 3I-ATLAS has proven that extraordinary discoveries remain not only possible, but inevitable in our increasingly connected and technologically sophisticated age. The viral spread of theories about its nature, ranging from legitimate scientific speculation to wild conspiracy theories involving alien reconnaissance missions, reveals that public hunger for cosmic discovery burns as intensely as ever. Each interstellar visitor becomes a cultural event that captures global imagination, inspiring new generations of scientists, engineers, and space enthusiasts. The social media response to 3I-ATLAS demonstrates both the promise and peril of conducting science in our digitally connected world. Legitimate scientific debates unfold alongside baseless speculation, creating information ecosystems where fact and fiction intermingle with sometimes bewildering complexity. Yet this same connectivity enables citizen scientists to contribute meaningfully to professional research, processing data, and making observations that supplement official scientific efforts. The philosophical implications may prove most lasting of all, fundamentally altering humanity's relationship with cosmic scale and galactic community. 3I-ATLAS demonstrates conclusively that our solar system exists within a galaxy where worlds routinely exchange material across interstellar distances, measured in light years. The organic compounds detected in its coma represent chemistry that occurred around alien stars, possibly orbiting stellar systems that died billions of years before Earth began its formation. We are literally receiving mail from distant cosmic neighborhoods, correspondence written in the universal language of physics and chemistry. Each interstellar visitor carries news from stellar environments we can never hope to visit directly, bringing samples of worlds and stars that exist or existed beyond the reach of even our most ambitious space exploration programs. This realization transforms our understanding of cosmic isolation. Rather than existing as a lonely oasis of complexity in an otherwise sterile universe, Earth participates in a galactic community where material exchange operates continuously across scales that dwarf human experience. The carbon in our bodies, the oxygen we breathe, the calcium in our bones all trace their ultimate origins to stellar nucleosynthesis that occurred in environments perhaps similar to those that created 3I-ATLAS. Looking ahead, the study of interstellar objects promises to become one of astronomy's most dynamic and revelation-rich fields. Each visitor offers unique insights into stellar environments we can never directly observe, planetary formation processes operating under conditions unlike anything in our solar system, and the deep history of galactic evolution that remains largely hidden from conventional astronomical observation. 3I-ATLAS arrived as a messenger from the ancient past, but it also serves as herald of a future where humanity routinely studies other worlds through the samples they deliver to our cosmic doorstep. The age of passive astronomical observation Studying distant objects only through the light they emit or reflect is giving way to an era of direct chemical analysis of interstellar materials. The universe has been sending these messages for billions of 2 years, cosmic postal deliveries that carry news from distant stellar neighborhoods. Only now have we developed the eyes to see them arriving and the wisdom to read what they contain. 3IATLAS reminds us that we live in an interconnected galaxy where discoveries await us in the darkness between stars, carrying stories of worlds and times that stretch far beyond our terrestrial imagination. Each future visitor will bring its own revelations, its own challenges to our understanding, its own expansion of what we consider possible in cosmic evolution. The universe delivers its secrets not through dramatic revelation, but through patient accumulation of evidence, sample by sample, visitor by visitor, building toward a comprehensive understanding of galactic diversity that will guide humanity's expansion into the cosmic community we are only beginning to recognize. In the end, 3IATLAS teaches us that wonder remains not only possible but inevitable for any species curious enough to watch the skies with patient attention. The cosmos continues to surprise us, to challenge our assumptions, to deliver visitors whose very existence expands our definition of what nature can achieve. We need only maintain the wisdom to recognize these gifts when they arrive, and the dedication to decode the messages they carry from the vast, ancient, endlessly creative universe that surrounds us. The secrets delivered by 3IATLAS represent just the beginning of revelations that await discovery in the cosmic correspondence that continues arriving at our doorstep. Each delivery brings news from worlds beyond imagination, written in the universal language of atomic structure and molecular bonds, waiting to be read by minds capable of appreciating their profound significance for our understanding of our place in the greater cosmic story.